Hello class, Mr. Bean here. This is video number 10 for AP Physics, Unit 3, Newton's Laws. This will be Section 5, Friction. So far to this point here, we have done problems involving the elevator problem. We have done problems with the pulley and also inclined planes. So kind of think to yourself here, at this point right now, am I able to solve for acceleration involving those three scenarios? Okay, if the answer is no, then you probably need to come see me or get some extra help. So now proceed. We're going to now introduce friction, and we're going to review the pulley problem, the inclined plane, and the elevator problem. This time with friction. All right, so let's take a quick look here and let's kind of see maybe what friction is. So here's an animation over here. Showing a chemistry book on top of a physics book here, and these could be molecules perhaps, or the two surfaces, okay, and they're not really touching, okay. So what happens is that, and here's a thermometer here, so if I go back and forth here, see what happens is that as I rub it here, go back and forth in movement, heat is generated. Okay, heat is generated. So friction does produce heat. Okay, and friction is what we call a non-conservative force. That means when we do our calculations, is force that's kind of like subtractive, is force that's lost, or energy that is lost and cannot be conserved. So think of it as the force before does not equal the force after. Okay, so think of it something like that. And we will discuss conservative forces in greater detail in this unit. But just to suffice, right now is two surfaces are rubbing. So we have to have two surfaces. They have to be moving. And as they move past each other, friction is created. And what is friction? Is the rubbing motion or generation of heat, or it could be there's like micro welds here that are being broken as the surfaces rub past each other. So that's kind of a brief example or a brief overview of what friction is intuitively. Okay. So back here is some more stuff here. Let me get rid of this here. Here we have some notes here, and let you go ahead and read this real quick while I go ahead and do a diagram here. And so friction usually involves two surfaces. So we'll call this here surface 1 here. And I'm going to draw these little lines like this to show that there's friction involved here. Okay, this is real world. And let's say there's a box here. And the box here will represent surface 2. So we'll go over here and we'll say surface 2. Okay, here's surface 2. All right, let's say the motion is going to be in this direction. Okay, motion in this direction. And we can assume that this is a center of mass, so the entire mass of this box can be concentrated right here at this point. So motion is going this direction, and what is friction, or how is friction coming about here? Well, here we have, of course, vector diagram of force. We have mg acting in this direction here, and up here we have the normal force acting in this direction. Okay, there's a normal force here. Okay, so what we have here is looking in the y direction here, we have some of the forces, right? In the y direction is going to equal 0 because there's no acceleration up or down. So when it equals 0, what we can conclude is that up is equal to down. If we do it this way, by convention, there's no negative sign. So up equals down. So the only force is going up here is the normal force. And the only force going down is mg. So what we have here is that the normal force equals mg. Okay. Now, the force of friction, if we want to talk about friction here, the force of friction is going to be given by this equation right here. So the force of friction is going to equal mu. There's this what we call a coefficient constant here of friction. Coefficient of friction is called mu, not to be confused with meow. Okay, and it equals Fn. Okay, and because Fn is mg, we can also write mu, force of friction as mu times m times g. Okay. Now, what is this mu? Okay. So this mu is a constant. Okay. It has a value ranging from 0 all the way to 1. Okay. Here's the range here. Okay. We'll kind of draw some arrows here. Now, over here, think of this as like oil on ice. Oil on ice. Okay, pretty slippery. Okay, that's down over here in this region. Over here, as we get closer to 1, think of sandpaper on sandpaper. So we'll say sandpaper, right? Sandpaper on sandpaper. Okay, sandpaper on sandpaper. So that gives you kind of an intuitive feel for this value here. Closer to 1 it is, the stronger the coefficient of friction is. Okay, and closer to 0, this more slippery it is, if you will. All right, so what affects what is friction? Okay, well, first of all, let me go ahead and use a different color here. So if motion is going in this direction, we'll say motion is going in this direction here. Friction is going to oppose motion. It has to be two surfaces that are sliding, and the motion is going to oppose, or friction is going to oppose motion. So friction is going to act in this direction here. We'll write F here with a little, I like writing a little F here for friction. There's the force of friction. Okay, so force of friction is going to oppose motion. Okay, and now back to this mu here. Okay, so mu, there's two kinds of mu. Okay, there's mu, what we call static, with an S here. That means not moving. Okay, it's not moving. Okay, not moving. And we have what's called mu kinetic. Okay, this is friction while moving. While moving. Okay, so there's two kinds of friction here, or coefficients of friction, when it's not moving and while it's moving. Okay, mu k is for kinetic, and mu s is for static. Okay, all right, and we'll talk about which one of these is greater. Well, actually, we can talk about it right now. So let's say, an example here, I have a dresser, and here's me pushing this dresser. Okay, so question. Is it in which case is it harder? Is it harder to get this thing moving? Okay, or is it harder once it's moving to keep it moving? So most people will agree it's usually harder to move a dresser from rest, but while it's moving, it's easier to push. So in that case, generally speaking, mu static, the static coefficient of friction is usually greater than or equal to mu kinetic, because it's always easier to push something while it's moving than to get it started moving. Okay, now up here, we'll let you look at this problem here, and it says you are pushing a refrigerator along a kitchen floor, and you need to apply 100 newtons to get it moving. If your refrigerator has a mass of 100 kilograms, what is the coefficient of friction? So it's at rest, so it means it's a static friction. So up here is the equation we're going to be using, and we're going to solve for mu. So what we have here is the force of friction, so is 100 newtons would go here. The normal force is going to be 100 times g, and g of course is 9.8. So if we solve for mu, we should get approximately 0.1. So this is a pretty slippery surface here. Okay. All right. So let's go ahead and go down to number 13 and 14 here. It says you're pushing a 15 kilogram box of books across a carpet. Okay, carpet. You need to apply 100 newtons. What is the coefficient of friction? Okay, so we'll go ahead and start off with this right here. So here's the force of friction. Let me go ahead and use a black pen here. And it's going to equal mu here, mu. And here we'll go ahead and write down the normal force like so. Okay, and you're pushing a 15 kilogram box, so that's the mass here. And you need to apply 100 newtons, so that's going to be the force of friction that you have to overcome. And what is the coefficient of friction? So here it's going to be 100 newtons. Okay, that's the frictional force that you have to apply to make it move. Okay, and this is mu. Okay, and it's 15 kilograms. So we have 15 kilograms right here, and we have 9.8 meters per second squared. Okay, so if I solve for mu, it's going to be basically 100 newtons here divided by, and we'll have 15 times 9.8, and that equals 147. 147 newtons here. So we'll go ahead and do that division here. 100 divided by 147, and it gives us approximately 0.68, and the newtons cancel out, so there's no dimensions here. So that's the coefficient of friction. I'll leave number 14 for you guys to do on Edpuzzle. Okay. Now down here, it says starting from zero, static friction. Okay, the two coefficients of friction correspond to two different physical processes. The first, called static coefficient of friction, applies to when you start pushing something from rest to get it moving. When you already have something moving and need to keep it, applying a force to keep it in motion, that's called kinetic coefficient of friction, which will be in the next section. Okay, the static coefficient of friction is usually larger than the kinetic coefficient of friction. Both have values between 0 and 1. So this is something we've already talked about previously. All right, and here's an example. We'll let you take a look at this example here. And we'll go ahead and take a look at number 15 here. It says you're standing on top of a ski slope and you need to apply 15 newtons of force to get yourself moving. If your mass is 60 kilograms, what is the static coefficient of friction? All right, so we have here mass is 60 kilograms, which is kind of easy. Okay, 60 kilograms. G, we're on the Earth, so we can go ahead and say 9.8 meters per second squared. Okay, so you need to apply a frictional force of 15 newtons. So the force of friction is going to be 15 newtons here. Okay, and it asks you what is the static coefficient of friction. So going to our equation here, here's the force of friction, which is equal to mu static times, we'll go ahead and write down mg here, and I'm going to go ahead and solve for mu static, and it's going to be the force of friction, which is 15 newtons here, right? The mass is 60 kilograms. We'll have 60 kilograms here. And we'll go ahead and say 9.8 meters per second squared, like so. And it's going to equal, we'll say here, 15 divided by 60 times 9.8, and that equals 0.025. Okay, so that's pretty slippery. So a ski slope, so it's ice. So this answer kind of corresponds with the ice here. Okay, we'll leave number 16 for you to do on Edpuzzle. Okay, now already in motion. Okay, kinetic friction. So you are already in motion. The second kind of friction is kinetic friction, which usually less than the force of friction you need to overcome static friction. Kinetic friction occurs when you push or drag an object that's already in motion. Okay, and so basically the equation is the same except for you have mu k here, which means kinetic. And here's an example. We'll let you go ahead and look at this example here, and then we'll work on number 17 here. So number 17, you're cross-country skiing and you need 20 newtons of force to keep going. If you have a mass of 70 kilograms, what is the kinetic coefficient of friction? Mu k. All right, so again here, the force of friction that I need to apply is 20 newtons. Okay, that's so I can move or keep moving, 20 newtons. My mass is, was it 70 kilograms? We'll go ahead and write it down here, 70 kilograms. And G, of course, is 9.8. So this is the given information here. And we'll go ahead and go, the force of friction is going to equal, now this time it's going to be mu, I'm going to put K here for kinetic. And here's mg. Okay, so mu kinetic, right, is going to equal the force of friction, which is going to be 20 newtons here, divided by the mass of 70 kilograms, okay, which is right here, 70 kilograms. And here we have 9.8 meters per second squared, like so. All right, so let's go ahead and do this calculation here. So it's 20 divided by 70 times 9.8, close parenthesis, and I should have 0, we'll say 0.03. So I'm cross-country skiing, and this answer here does make sense. All right, we'll go ahead and let you do number 18 on Edpuzzle. All right, so this next part here is static friction along a ramp. So we're going to tie this into our inclined plane problem. Okay, the inclined plane. So let's take a look at this. Let's go ahead and let's go ahead and draw an inclined plane, and we'll kind of draw it like this here. Okay, and of course this here is theta. So here's theta, like so. And suppose, let's say we have a box here, and a box is resting along here, and it's not moving. Okay, it's not moving here. And let's go ahead and let's identify all the forces now. These are all the forces that are acting. So it's called a free body diagram. Let's go ahead and do a free body diagram. This is very big on AP tests, and just in general, we should understand what the free body diagrams are. So we do have mg acting like so. We have mg. Okay, we have the normal force acting in this direction. That's the normal force here. Okay, and then we also have the force of friction, which is acting in this direction here. The force of friction. Well, if it was moving in this direction. So if it's not moving, that means that, so these are the only three forces that are acting. Force of friction, normal force, and mg. Now, let's say this is not moving. Okay, so we'll say acceleration is 0. Therefore, velocity is either going to be 0 or velocity is constant. Okay, velocity is constant. Okay, so let's say it's not moving. All right, now here I'm going to draw the components of force of gravity. So here we have the parallel force. So the parallel component of gravity is acting down this direction, and we also have a perpendicular component of gravity. We'll call this the perpendicular component of gravity. Now, the parallel component of gravity, I'm going to use black here. Remember, the parallel component is going to be mg, right? mg, sine of theta. mg sine of theta. Okay. All right. So now, okay, and also let's take a look at our frame of reference. We have y is like this, which is positive in y direction, and here we have, so it's kind of like this here. So this is our x component right here. X is going this way. All right, so let's take a look at the y direction here. There's no motion in the up or down direction. So if we were to go sum of the forces here in the y direction, right? Sum of the force y direction, it equals 0. Okay, so that means that up equals down. Up equals down. All right, so the only forces that's going up in the y direction is going to be the normal force. Okay, the only force going down is going to be this perpendicular force. So the first force perpendicular, the perpendicular component of gravity. Okay, now what does that equal? Okay, the force perpendicular is going to be mg cosine of theta. Cosine of theta. So let's go ahead and write this, make this a little bit better here. So the normal force is going to be mg, right? Cosine of theta. Cosine of theta. Now, if if this was flat surface, theta would be 0, and the cosine of 0 is 1, so the normal force would just equal mg. So on our inclined plane, or on our ramp, the normal force is given by mg cosine of theta. Now, how do we tie that in to the frictional force? Well, the frictional force, or the force of friction, is going to be mu, right, times the normal force. Now, we're on an inclined plane, so if the theta is not 0, it's going to be mu mg cosine of theta. mg cosine of theta. So this is the force of friction when you're on an inclined plane and theta is not 0. Okay, this is the force of friction. All right, now let's go. So this is our analysis of the y direction. Now let's take a look at the sum of the forces along the x direction. Okay, now as we said before, it's not moving, so it's at rest. Okay, so we can say sum of the forces is equal to 0. Acceleration is 0, that means velocity is 0, or velocity is constant. So it's not moving. So velocity, so sum of the forces in the x direction equals 0. Okay, what does that mean? That means left, right? Left equals right. Left equals right. All right, so what's going left here? So we have the parallel force, which is mg, right? Sine of theta. Mg sine of theta. Okay, what's going to the right? We have the force of friction. Okay, and the force of friction we know is mu mg cosine of theta. Okay, now if I wanted to, I could have said the parallel force of gravity is equal to the force perpendicular, or the force of friction. Force of friction. There we go. All right, that's what I should have done first, and that's where these come from here. So now back up here, what cancels out? Looks like mg cancel out. Mg cancels out here, and I have the sine of theta, right, is equal to mu. Now, it's going to be static because it's not moving, and here we have cosine of theta. All right, so now, if I want to, now take a look here. This is interesting here. Mu static is going to equal the sine of theta divided by the cosine of theta. So from trig, sine divided by cosine is the tangent of theta. So sometimes a real quick way to figure out if something's not moving is to adjust the ramp to just when it begins to slide. We can quickly figure out the static coefficient of friction by doing the tangent of theta. That will get us the coefficient of static friction. This is kind of the quick and dirty way to do it. All right, we'll go ahead and pause here. All right, so let's go ahead and do another example here. Suppose that here we have a widescreen TV's box has a mass of 100 kilograms and the ramp has an angle of 23 degrees. What is the force needed to get the box moving up the ramp if the coefficient of static friction is 0.2? So let's take a look and see what's going on here. So here we have a ramp, and the ramp, let's say, is 23 degrees. So we'll go ahead and put down 23 degrees right here. And here's this box here, or this TV screen box. And what force is needed to get the box moving up the ramp? So motion is going to be in this direction. We have to apply a force in this direction to get it moving. So if it's moving in this direction, friction is going to be moving in this direction. So friction is moving in this direction here. So here's a force of friction. Now, there's also another force that's always present here. Okay, we can't ignore this force. So in addition, because it's moving up the ramp here, there's also a force going this direction, which is parallel force. The force parallel is always acting down the ramp. Okay, so this force has to overcome both friction and the parallel force. Okay, all right. So let's go and go to the black pin here. All right, so So the question is, what force is needed to get the box moving? All right. So we're only concerned about the x direction in this motion in this direction here. So we'll go ahead and call it up the ramp. We'll say what force is needed, and we'll say it's in the x direction, and it has to overcome the force of friction, and it also has to overcome the force parallel, which should be a plus sign here, and the parallel force. Okay, let me go ahead and erase this real quick here. Let's get this a little bit better. And there we go. So it has to overcome both the frictional force and the parallel force. Okay. So right now it's not moving. So we'll go ahead and take a look here and see what we got. So the force of friction is going to be, was it mu, right? mg cosine of theta plus the parallel force, which is mg sine of theta. So this is the force needed to overcome it, okay, or to get it moving. So now, once we're here, we can go ahead and plug in the values. What is mu? Mu is 0.2, so 0.2 is mu, okay, and the mass of this is 100 kilograms. We are on the Earth, which is 9.8 meters per second squared, like so. And we're going to have to do the cosine. Now make sure we're in degrees, not radians. Cosine of 23 degrees here. Plus, now if you want to, you can put this in a bracket here so we don't get confused with our math here. Another bracket here. And we have the mass again is 100 kilograms, like so. Times 9.8 meters per second squared, like so, times close parenthesis, times the sine of 23 degrees. All right, so we do all of this work here, and we should get about 562 newtons. So this is the force needed to get the box moving up the ramp. Okay. All right. And we'll go ahead and let you do 19 and 20 on Edpuzzle. Okay. The next part here is kinetic friction along ramps here. Okay. So kinetic friction. All right. So now this time, here's an example here. And we'll let you work through this example here. But I'm going to go ahead and focus on number 21 here. So it says you're dragging your little sister up a 25-degree wheelchair ramp at the doctor's office. If she has a mass of 30 kilograms and a coefficient of kinetic friction mu k is 0.1, how much force will you need to apply to keep her going? All right, so let's take a quick look here. Here's our ramp here. And this could represent little sister here. Okay, so you're going to be applying a force in this direction here, right? So this is the force that you're going to have to apply. But because we have friction, you have to overcome both the parallel force, the force parallel, the component of gravity, and also the force of friction. So you have force of friction and the parallel force to overcome to keep it moving. All right. So this time here, how much force will you need to keep it going? All right. So we'll go over here and we'll say the force needed again is going to be we'll say force parallel and the force of friction. So you have to overcome both of these. And here we have force, and this is going to be mg sine of theta plus mu mg cosine of theta. So plugging in all of these values here and 9.8 for G, the force should come out to about 150 newtons. All right. So on Edpuzzle, I'm just going to have you do number 22 and perhaps number 24 here. We'll let you do those on Edpuzzle. All right. Last thing here, and then we'll conclude this video. Here we have acceleration on long ramps, including friction. Okay, so it says here, suppose that you have a block of ice that has been mistakenly placed near the top of a long ramp and it starts sliding down the ramp. The preceding section helps you calculate how much force acts on the block of ice. So how about calculating the acceleration down the incline? So before we were talking about the force on the ice, how about calculating the acceleration down the incline? Okay, so that's a good question here. We want to figure out what's the acceleration. All right, so here's an example. We'll let you go ahead and look at this example here, and I will work out number 23 here. Okay, it says here you're dragging a suitcase up a ramp onto a luxury hotel when it gets away from you. If the angle of the ramp is 31 degrees and the kinetic coefficient of friction is 0.1, what is the suitcase's acceleration down the ramp? Okay, so let's take a quick look at that. And let's make a incline plane here. And here we have this box here. So this time the motion is going to be down the ramp. Okay, so motion is down the ramp. Okay, and here's theta, and theta is 31 degrees. Okay, so when it moves down the ramp here, let's identify all the forces acting. All right, so first of all, we do have a parallel force component of gravity, which is right here, the parallel force right here. And we also have a force of friction now is going to be acting in the opposite direction. So the force of friction opposes motion. All right, so, and it's also accelerating too. Okay, so let's take a look at what we're going to be doing here. So this time we're going to do sum of the forces in the x direction equals ma. So it is accelerating. Okay, so velocity is not zero or it's not constant. All right, so let's take a quick look here. And so we'll say down the ramp is positive and up the ramp is negative. So friction will be negative. So we do this here. We have the parallel force here, right? Minus the force of friction, which equals ma. All right. So we'll take a look here. The force of the parallel force is going to be mg, right? Sine of theta minus mu mg cosine of theta, which equals ma. Now, if you look closely, the mass here, here, and here can cancel out. So if we were to do this here, we would have here 9.8 times the sine of 31 degrees minus we have 0.1 is the coefficient of friction times 9.8 times the cosine of 31 degrees, which equals acceleration. So if I do the calculations correctly here, I should have 9.8 times the sine of 31 minus 0.1 times 9.8 times the cosine of 31. And close parenthesis equals 4.2. So the acceleration I got is about 4.2 meters per second squared. Okay. All right. All right, so that's number 25 here. 26, 27, and 28, we'll go ahead and do these in class. All right, so look forward to seeing you in class, and good luck. Talk to you guys later.